Welcome to the deep dive. Today we're plunging into something pretty astonishing, a whole new class of cosmic explosions. I mean, imagine events so powerful they just outshine anything scientists have seen before, and they last for years.
When I first read about this, I just couldn't quite wrap my head around it. Years for an explosion. It seems unlikely.
It really is groundbreaking stuff. What we're talking about today are called extreme nuclear transients, or ENTs for short. And this is all based on some really exciting new findings. Came from astronomers over at the University of Hawaii's Institute for Astronomy, the IFA, just published in Science Advances. Right. So our mission then for this deep dive is to really unpack what these ENTs are. How were they even spotted? And I think crucially, why are they kind of reshaping how we think about supermassive black holes and, the really distant universe?
Okay, let's start right there. What exactly are we talking about with these ENTs, these cosmic behemoths? So at their heart, it happens when a supermassive black hole just completely gobbles up a giant star. And when we say giant, we mean, huge, like at least 3 times the mass of our own sun. That's a lot of star.
Yeah, and that's the really key difference here. We've known about tidal disruption events, TDEs, for a while. That's where a black hole rips star apart. But ENTs, the lead researcher, Jason Hinkle, he put it nicely. ENTs are different beasts. They get nearly 10 times brighter than your typical TDE. It's not just a bit brighter. It's a whole different scale of luminosity. Wow. And it's not just that peak brightness either, is it? It's how long they keep it up. You mentioned TDEs or supernovae. Yeah. They flare up, then fade pretty fast usually. But these ENTs, they apparently remain luminous for years. Years. That just surpasses the energy output of even the brightest supernovae we know. How does that even work? How do they sustain that?
Right, exactly. So unlike a supernova, which is, one big bang, one catastrophic event, ENTs seem to be caused by, let's say, a smoother, more drawn-out process. It's the massive star being kind of slowly consumed over time by the black hole. This sort of continuous feeding, if you will, lets the event pour out energy for much, much longer. And what's fascinating, kind of a paradox really, is their rarity versus how useful they are. ENTs are extremely rare, like millions of times less common than supernovae.
Millions. Yeah.
But, and this is the crucial part, they are so incredibly bright that brightness means we can actually detect them in galaxies billions of light years away. So even though they're rare, their sheer power turns them into this amazing new tool for probing the distant universe.
Okay, speaking of detection, the story of finding one specific ENT, Gaia 18CDJ, sounds pretty dramatic. The energy release you mentioned, 25 times more energy than the most powerful supernova ever recorded. That number is just staggering.
It really is. Let me try to put that into perspective. Gaia 18CDJ, in just 1 year, gave off as much energy as, get this, 100 suns would emit over their entire lifetime.
100? Wow!
Yeah. Compare that to a typical supernova that matches the output of maybe 1 sun over that same year. So you think about our sun. Everything it does for us, its entire life's energy, multiplied by 100, squeezed into 1 year from one event. It's, it makes you pause.
It really, really does.
Yeah.
So how did Jason Hinkle actually spot this? He was looking through data from the Gaia Space Telescope, right? What was it in that mountain of data that jumped out and said, hey, look at me, I'm different?
Well, Hinkle himself said, Gaia observations don't tell you what a transient is, just that something changed in how bright it appears. Makes sense. But, he said, when I saw these smooth, long-lived flares from the centers of distant galaxies, I knew we were looking at something unusual. So it was that smooth, very long duration brightness change. That was the key signature that didn't fit the known patterns. That intuition plus the data pointed to something new.
Okay, so they spot these weird long flares, but then they had to be sure, right? Prove they weren't just some odd supernova variation, or maybe just normal, albeit dramatic, black hole activity. You mentioned they used a ton of observations, like years of data from UH's ATLA system, those telescopes on Halakala and Mauna Loa, and Keck on Mauna Kea, other telescopes too.
Absolutely. They needed confirmation from multiple sources, multiple wavelengths. It was a huge effort. And all that data helped them build a picture of the physical process. As we were saying, it points to that smoother, more drawn-out process. You can sort of visualize it. The star gets stretched by these immense tidal forces near the black hole. Eventually, it gets ripped apart, and the material forms this swirling disk, an accretion disk, feeding the black hole. And interestingly, they also inferred this dusty torus, like a big donut of dust and gas, around the black hole and the disk. They figured that out partly from detecting an infrared echo light bouncing off the dust. This whole detailed picture confirmed it wasn't just a simple explosion.
Right, the echo from the dust. That makes sense. And the brightness during all this, you said it outshines the entire stellar output of its host galaxy for nearly a year before it finally starts to fade, like after more than a year as the feeding slows down. Just incredible luminosity.
And that's where we get to the sort of so what question, the broader importance. Benjamin Chappie, one of the co-authors, pointed out they give us this valuable new tool for studying massive black holes in distant galaxies. If we connect this to the bigger picture, yeah, this is really crucial for understanding how the universe evolved.
Because they're so bright, we can spot them incredibly far away. We're talking billions of light years, which means, well, because light takes time to travel, looking that far away is literally like looking back in time, isn't it? We're seeing light that started its journey when the universe was much, much younger, maybe half its current age.
Exactly right. It's cosmic archaeology in a way. By studying these really long flares from so far away, scientists get these unique insights into how black holes were growing back then, back when the universe was maybe half as old as it is now. And galaxies were, well, busier places. They were forming stars like crazy, feeding their central supermassive black holes about 10 times more vigorously than galaxies do today. So, yeah, it raises this really important question. What else can these ENTs tell us about those really formative cosmic years?
Okay, so let's wrap this up. Extreme nuclear transients. They're not just, spectacular fireworks in space. They're acting as these crucial beacons, letting us probe the biggest black holes and look way back into the early universe. I think Jason Hinkle summed it up perfectly. These ENTs don't just mark the dramatic end of a massive star's life, they illuminate the processes responsible for growing the largest black holes in the universe. That's powerful.
It really is. And the future looks even more exciting for this field. Astronomers are really hopeful. Upcoming observatories like the Vera C. Rubin Observatory, NASA's Roman Space Telescope, they expect these will find many, many more ENTs. It could genuinely revolutionize our picture of how black holes grew in the early cosmos.
So what does all this mean for you listening right now? Maybe it's a reminder that even in these incredibly destructive, violent cosmic events, there were these brilliant new clues just waiting, clues that help us piece together the huge, grand story of how our universe came to be. Makes you wonder, doesn't it? What other secrets are out there just waiting for the right light to shine on them? Keep watching the skies, I suppose.